As I said in the website iol.unimo.it, you can find now 2 more links to lectures. This is not very relevant, but also you will find there the first self-assessment test. Okay, self-assessment test. It's something 8 questions, not many, just done, and it's new. You can take it if you want. I think it's a good check for you. It's a good option to check whether you are prepared. Of course, if you keep the web page open on another window of the PC, it's very easy to make it. So I suggest that you try when you feel that you are a bit prepared. They are just basic questions. You try the test without looking at the web page while you are doing the test. You can repeat it, so you can try whenever you want. The only thing that I wanted to ask you is, given that it's new, and I didn't double check it, I just would like to get your feeling, like if you feel that the questions are clear, and if you feel that the feedback is reliable. I'll try to make it myself, but given the system doesn't give me the full identity of a student, and therefore it's difficult for me to test it. And so just if you try and give me your feeling, this would be much appreciated. As I said, I think it's a good idea if you try it. Okay? Okay, let me move forward. We were talking about flow duration curve, and which is abbreviated with the acronym FDC. And if you remember, we already introduced a procedure for computing it. I am not repeating it. We said you just have to get the observations, for instance, daily observations for 1 year, put them in descending order from the highest to the lowest, and then if you plot these observations against their position in the record, you get the flow duration curve. Okay? And what you get is something that is like this. If you, of course, display the flow in the ordinate and the duration in the abscissa, which is a convention which is usually applied in Italy. And you know, this is something that is a bit strange because the independent variable is flow and the duration is the dependent variable. So you would expect that you plot the duration in the ordinates rather than in the x-axis. Indeed, in some countries abroad, they use this convention of putting the duration on the ordinate. Of course, it doesn't change anything. It's for historical reason that it doesn't change anything from a conceptual point of view. It's for historical reasons that in Italy it is depicted in this way. But of course, you don't have to be concerned on the convention. You just have to try to fix on the concept, which is unchanged, of course. And you get something that may look like this. This is the duration of 365. As I said, I am just plotting. I am sorry, I have a bit of a cold. I am just plotting the observations of river flow from the highest to the lowest, depending on the position in the record, in the order, the rank, the record. And you get, as I said, something like this. But you may get also different shapes. For instance, I am plotting on the same graph. You may get something like this, for instance, with the FDC crossing the abscissa at a certain duration, which means that the observations are 0 for the remaining days. If I am crossing the abscissa at the duration 100, for instance, it means that for 100 days I observed some flow in the river. For the remaining 265, I didn't observe any flow, which means that the river is, we say, it's intermittent. And you may get also other shapes like this one with the same maximum and the same minimum. You may get something like this, or something like this. Okay, Okay, usually you don't get a so steep shape in the longer durations, but you may get with the same minimum and same maximum different shapes. Okay, remember that the area that is below the flow duration curve, here is another one, QTD. The area that is below here, it's what? This is the integral of the curve. So the area in yellow, it's equal to the integral between 1 and 365 of QT in the T. Correct? Where with T, I am indicating the duration, in this case, time. Therefore, what is the integral of Q over T? Remember that Q is river discharge or river flow. It's volume of water per unit time. So if I integrate over time, I get the volume, which means that the area in yellow is the annual volume of flow and therefore you understand that different shapes in the flow duration curve imply, of course, different volumes of flow. The lower blue curve implies that the flow volume is reduced. The upper blue dashed line implies more volume. Okay? And therefore, you can easily understand that by looking at the flow duration curve, you get immediately an idea of the river flow or the river regime, we call it. Regime is defined, the river regime is defined as the average river flow in the different seasons. So you get an idea of what? Volume of water. You get an idea about intermittency, possible intermittency. You get an idea of the low flows. You get an idea of the high flows, but not flood flows. The flow duration curve doesn't tell you anything about flood flows unless some assumptions are satisfied, which we don't discuss here. What is the reason why the flow duration curve doesn't tell you anything about flood flows? Because we define flood flows, those flows that occur once in every, depending on the definition, but 30, 50, 100 years. So if you have just 1 year of data, like in this case, you don't get an idea of flood flows. You get an idea of the high flows in that year, not more. Good. Okay. Also, if you in the web pages there is a figure that clarifies, and I want to use the same terminology. Clarifies, it defines, it subdivides the duration in intervals, in subintervals, and says that here in the very first interval of duration, from 1 to 10 days, it uses the term flood flows to identify the flows that correspond to this duration. Again, this is not very precise, so don't use flood flows, just use high flows, like it is depicted in the figure for the second interval, and then we have intermediate flows and the low flows here in the final part. So, I would say that the flow duration curve gives you an idea of high flows, intermediate flows, and low flows. But just for 1 year, and this is a limitation, because when we want to design an infrastructure, a water supply system, a water system, usually we design for an expected lifetime, which is something variable between 10 and 500 years. And therefore, you need to get an idea of the river regime in the long term. So what I want to stress here now is that I made an example of computation of the flow duration curve referred to 1 year. And this is for teaching purposes. But actually, you don't want, for design purposes, to estimate the flow duration curve or estimate water resources availability, which is our problem, on the basis of only 1 year of observation. Usually, you want a longer observation period, and the reason is clear, it's obvious. You want to get an idea of the river regime in the long term. So, now the question is, from an operational point of view, given that I need more than 1 year of data, how can I estimate the flow duration curve? This is quite intuitive, but let's discuss it, because we have two possible options. So if we have only 1 year, the option is just this one, which I introduced, but it's not very useful. So actually in practice, you have to look for more data. So let's suppose that you have many years, and let's see how we can move forward in this case. So let's suppose that we have 10 years of data, okay? I say 10 because usually this is the indication that we engineers give. So if the question of the student is, how many years of data do I need to estimate a reliable flow duration curve? The answer usually is about 10 years, which is, you know, a kind of rule of thumb. Do you understand what is a rule of thumb? It's a basic rule. Actually, there are studies that prove that even with 2 years of data, if you don't have much variability, you get a reliable estimate. But actually, it depends on the expected lifetime of your infrastructure. If you are designing for an expected lifetime of 100 years, you know, even 10 years are too few. So you have to consider your expected lifetime of your design, and ideally, you should get an observation period whose length is comparable to the lifetime. Comparable means that, okay, if it's half of the lifetime, it's comparable. If it is 1/10, if it is 10%, you know. So if you design a bridge, expected lifetime is 200 years, and you get the estimate, the design variables on 10 years observation period, this is a bit odd. If something happens, the court may tell you, because you know the engineer is brought in front of the court when something happens, and your responsibility could be a bit relevant, because the judge could say, you know, your observation period was too low. Okay? Of course, if you design a sewer system whose expected lifetime is shorter, then that's fine. Maybe that even 2 years is fine. Of course, when you design a sewer system, your design variable is not derived by the flow duration curve. It's just a general concept that I'm trying to illustrate to you. Okay, so let me go back to the very question that I introduced. 10 years. Let's suppose that we have 10 years of daily observation. How to estimate the flow duration curve? That's fine. And let's use the same procedure. But we have 3,650 data. Let's forget the leap years. Let's forget the February 29th. Let's remove them. In 10 years, we have, again, 3,650 data. Let's order them in, again, from the highest to the lowest. Okay? So, basically, I get a column in R or Excel, whatever, of Q. And this column of Q is ranked from the highest to the lowest. Okay, and then let's give a number here, from 1 to 3,650. Remember the definition of flow duration curve. The definition is, for each observation, I should plot the percentage duration. So it's very easy to understand how I have to determine my abscissa. It's just to translate this in percentage term. This column from 1 to 3650, let's transform it in percentage terms. If you want a duration still expressed in from 1 to 365, like we do in Italy, usually, even if we compute the flow duration curve for 100 years, we want to express the abscissa from 1 to 365. This is easy. You just have to divide this rank here 1 over n, where n is number of years. Okay, so here you have 365, because n is 10 in our case, so 3650 divided by 10 is 365. If you want to express it in percentage terms, it's very easy, and you know how to do it. That's clear? Look, if I use this procedure, what I got is a definition of the flow duration curve for duration that is below 1 day. And therefore the graph, it's preferable that we start it from 0, not from 1, in terms of duration. Let's put the origin at 0 duration, because here I have the opportunity, again, to estimate the flow for duration that is lower than 1 day. Everything is clear? Okay. Good. Now, I anticipate to you, I asked you 5 minutes more, and during these 5 minutes I will ask you, and this is compulsory, to ask me at least 2 questions, so take notes, okay? If you have questions, keep them for the last 5 minutes. You can ask questions even now, but today, as a kind of interaction, I want to stimulate this, okay? So again, this is one possibility, and keep in mind, in this case, if your observation period is long, let's suppose 100 years, like for the Po River, 90 years, the highest value of flow, indeed, is something that can be called a flood flow. So in this case, when your observation period is long, you can indeed say that in the first part of the curve, typically for durations much lower than 1 day, you can say that your flow duration curve gives you an idea of the flood flows. So, in summary, it's not a mistake what is depicted in the figure that you see on my website, where they call these very high flow flood flows. But keep in mind that not necessarily the flow duration curves give you an indication of the flood flows. It can give it only if the duration is much, much lower than 1 day. So again, the figure is not mistaken, but it's a bit, we need to be aware that in general, when we talk about estimating flood flows, we don't use the flow duration curve. We don't use it because not necessarily it gives to you such estimate. So the flow duration curve that you obtain in this way gives you an indication of the average behavior of the river during the observation period. That's fine. It's an indication of the average because your observation period is very long. I'm sorry, my pronunciation today, because the cold gives to me some difficulties in pronouncing. In Italian not, but in English, don't understand why. Okay, so, as I said, it's an indication of the average. Now, keep in mind one limitation. no indication of variability. So you get this curve, which is an average curve that you get for 100 years observation period, but you don't know from 1 year to the next what is the variability of the curve around the average, which is an important indication for a water resources manager. Very important, because an average indication of the river flow that we can get from a river, of the river that we can withdraw, of the water that we can withdraw from a river, an average indication is fine. But we need also to know what is the variability of this average, because if the river flow is constant, the indication of the average gives an indication of everything. But if it is not constant from 1 year to another, of course, I'm not sure to get the average flow in 2019 from the Po River. I'm not sure to get the average because I don't have an indication on the average, on the variability. Okay, so this gives to me the opportunity to introduce a second method for estimating the flow duration curve, which is very simple. If you have 10 years of data, instead of estimating the flow duration curve in this way, let's estimate the flow duration curve for each year, therefore computing the so-called AFDC, annual flow duration curve. AFDCs. This is reported in my web pages. And then I make a plot where I get not only one curve, but I get one curve for each year. So the first one may be this. Let's now put the abscissa between 1 and 365. I start from 1 because this is computed to 1 year. Okay, then we get another curve, which may be this one. And then another one. And then again another one. For 10 times. Okay, good. Then for each duration from 1 to 365, we can compute the average. So, for instance here, let me recover the red color because I want to use the red color for the average. Orange. Okay, here I can compute the average, and the average is something like starts from here and then passes from here and then here, here, here. So it's something like this. Okay, and it's the thick orange line. Good. So this is my average, which is very similar to the curve that I derived with the other methods. If you compare them, they are almost overlapping. Good. But then I estimated not only the average, I have an estimation also of the variability around the average, which is what I'm looking for. An indication that you can give to the customer is, for instance, 80% of the time, the flow duration curve is comprised in a given interval. So you estimate an interval, which is something like this. Thick blue lines. Or the second one, I use the dash. You estimate an interval, this interval here, such that you can tell your customer 80% of the time you get a flow corresponding to a given duration that is included in this range. This is a very good indication because it gives an idea of variability. If the range is very limited, very narrow, then there is not much variability. If the range is wide, there is a lot of variability. And how can you estimate this range 80% of the time? Very easy. If you have 10 curves, for each duration you have 10 values of flow, you reject the highest and the lowest. So you reject 2 over 10, and then you get an estimate between the second and the ninth. You get an estimate of the 80% of the times. Of course, it becomes more reliable if you have 100 years, and then you reject the upper 10 and the lower 10. Oh, this is quite interesting. What is the disadvantage? With respect to the previous method, of course you gain more information, and given that the data that you have are the same, you may expect that you lose some information. What are we losing? We are precisely losing the definition, the resolution. With the first method, I told you, for instance, I can estimate the flow for duration lower than 1 day, and I can estimate the flow for durations comprised between 1 and 2 days. So I have a finer resolution. In this case, I have for duration 1, 2, 3, in between, I don't have anything. Between 0 and 1, I don't have any information. Between 1 and 2, I don't have any information. Here I have information between 0 and 1, between 1 and 2, and so forth. So I lose the resolution. It's a coarser resolution in this case, but I gain information on variability. So the information that I first put in the resolution, now I am putting it into an estimate of variability, which is nice. It's a different way of extracting information. Again, this is nice. Okay.
So in the first method, you don't have any information about variability?
Yes.
Okay.
No, because you get only one curve.
Ah, okay, okay.
It's just one.
Ah, okay.
It's just one with a finer resolution.
Ah, okay, yes.
Okay.
Because you still have the highest and the lowest. You don't discard any value. That's the reason why.
In this one, I don't discard any value.
Yeah. Okay.
Okay, because I don't need to discard them, because this is an estimate of the average. When you estimate variability, even in this case, you may decide not to discard anything. But usually when we present estimates of variability to our customers, we define variability as a percentile range. So this is the way customers usually like to get it. Like, okay, I want to be sure at 80% percentile, and therefore, for this reason, I want to discard but you may also say, okay, for the observation period, I don't discard anything. This may be another choice, but if you don't discard anything, you know, I think it is too safe estimate. Usually the customer doesn't want complete safety. Complete safety doesn't exist, but they want an estimate of the risk, but usually they accept some risk. So this is why...
Because of economical reasons.
Yeah, for economical reasons, yeah, for sure. Because of course, if they design the infrastructure with more safety, then it becomes less, the benefit, part of the benefit is lost. It's more costly and part of the benefit is lost. Because we will talk about, for instance, hydropower plants, and you will see that the optimal design of the plant is for the design flow. The plant works well at the design flow. And if you lower the design flow, because you want to make sure that the plant works for 100% of the years, then when you have more water, then the plant doesn't work efficiently. So they lose some money if they want to get safety. Okay, so one final thing. I mentioned to you last week that when we estimate the duration in percentage terms, not in absolute terms, when we estimate the duration in percentage terms, we should divide the rank, the number assigned to each observation, by n. This is in percentage term. If I divide not by n is number of years, by m, number of observations. If I divide here each observation by 3650, I get a duration from 0 to 1. This is in percentage terms. But last week I told you that if we indicate the number of observations with m, m is sample size, we call number of observations in statistics, we call it sample size. So if we divide, usually we don't divide by m, but we divide by m plus 1. And this, I told you, let's discuss this later. Take it for granted and we will discuss it. Now I want to explain you why, instead of dividing by m, we divide by m plus 1. And the reason is that we don't want to give to the lowest observation, we don't want to give it a duration of 1. Because keep in mind that the flow duration curve is conceived for estimating low flows more than high flows. And if we give to an assigned value of flow, of low flow, a duration of 1, it means that we take for granted that in any condition, this is a flow that will be always equaled or exceeded. This is a flow that will be available forever. Duration 1 means that that flow is always equaled or exceeded. So if we go to a customer and tell the customer a value of river flow for duration 1, the understanding of the customer is that that flow is available forever, which is not a good indication because, you know, we handle data taken from an observation period. Tomorrow is another day. It's another day that is not included in the observation period, and it may happen that tomorrow the river flow is lower than the lowest that I found here. So we may tell the customer, look, this is the river flow with duration 1, and the day after, the customer comes back and says, look, today I don't have that river flow. What happened? So what is a way for protecting and then for giving a safer estimate? What is a way for allowing us to say that we cannot estimate the river flow with duration 1? We cannot, because our observation period is always finite. The solution is this one. We divide by n plus 1. We don't get whatever the length of the observation period. We get very close to 1, but we never get to 1. You see that if m increases, and this is not 1, actually, it's I, okay? It's I. It's varying with 1, I is comprised between 1 and m. If you look here, from 1 to 3650, this is my m, okay? So, you see that for increasing m, you get very close to 1, which is what you expect, but you don't reach 1. This is something that in statistics is extremely important. So we don't say, we never say that we are certain about a value. We use the same procedure for flat flows. We don't say to a customer, this flow will never be exceeded. We say, will never be exceeded with a probability that is very close to 1. Okay. For moving forward, keep in mind another thing. I'm talking now about frequencies. Basically, these are frequencies. The flow duration curve depicts frequencies of flows. What I'm talking about here, these graphs, it's frequency. Because duration means, duration can be expressed in relative terms. So a frequency of 0.5 means that on average once every 2 observations I have this event. No? When I say I toss a coin 10 times and I have a frequency of heads that is equal to 0.5, it means that about half of the attempts I expect that outcome. So I'm talking about frequencies. Just keep in mind, okay? And keep in mind one important thing that removes a lot of hassle from you. Frequency, we may say, as engineers, a statistician would be horrified by what I'm saying. But as engineers, we can say that frequency equal probability. Okay? So, when, as an engineer, when you hear someone talking about probability, immediately associate probability to frequency, and everything becomes much clearer, much and much clearer. Because we engineers, understanding probability is not easy for us. So we need some tricks, and this is an excellent trick. But as I said, be careful if you speak with a statistician to say, oh, okay, this is frequency. She would be horrified. Okay, so, but to give you the concept, I'm talking about frequencies, probability. So this range here, 80%, you can say to a customer with probability of 80%.